All right, we're back. We are still on page 130. We just did some problems involving finding the angle between two vectors. We did it in radians. We used a calculator for like a lot of it because I wimped out and didn't want to do magnitudes and I didn't want to do dot products by hand. But you know what? You got to know how to use a calculator too. So, it was a wimpy move, but whatever, we'll survive. Let's see what this says. Find at least two vectors orthogonal to each of the following. Just figure it out. 2D is cool like that. That's true. So in 3 dimensions, you got to like think a little more. Here we don't need to because all we really need to do is work out like what would make the dot product 0. So take a look at this first one, right? 315. What would make the dot product 0? Well, what if, bear with me, what if I just switch them? Does that make the dot product 0? It does not at all. But what if I switch them and change the sign of one of them? Now I'm doing 3 times 15 plus 15 times negative 3. Guaranteed that's going to give me 0. That's a good move. That's the textbook two-dimensional trick, is you switch them and change the sign. So what I'm going to do for the next one is similar. I'm just going to multiply through by a negative here. So I'm going to use negative 15, 3, right? Because so basically what happened here is that we have our one vector. And the first thing we did was create this vector. And then the next thing I did was create this vector. I just reversed drawn all over. I just reversed the direction of it. Like, why would that not make it orthogonal? It's still going to be orthogonal. So that definitely worked. I think that I can use that trick on this also. So I think I can do like 4i minus 6j. And then I also think that I can so that would be 24 minus 24, definitely 0. And then why not multiply this by a negative? So negative 4i plus 6j. So this is just to like get you in the spirit of doing this. Finding a vector orthogonal to another vector is a big deal. It's an important thing, but it's not a huge challenge. And you just have to get used to it. So this will always work. You could also, so you can do your own thing, right? So 315, for example, I could just say like 315 dot, I don't know, x comma 2 has to equal 0. So that would be 3x plus 30 equals 0. So x is negative 10. And I'll use the vector negative 10 too. That's totally an option. You could do that. You could say like 315 dot 25 comma y, and then solve for y. As long as you only have one degree of freedom, one thing you don't know, one variable, you'll be able to solve that every time. So that's also a way you could approach it. I just don't think you need to in this case. All right. Now, 18 okay. One thing, dot products that are orthogonal vectors, rather, the magnitude of the vectors doesn't really matter. Like, you could be using the unit vectors and they'll be orthogonal, or you could take the unit vectors and scale them up to like 3 trillion. Not going to change the angle between them. So what I'm saying is this 18, no one cares. Just ignore it. Get rid of it. Doesn't make a difference. The magnitude of the vectors in question does not make a difference. So for example, here, I could change this to 5, negative 1. And then 5, negative 1 would just give me 3 times 5 is 15, 15 times negative 1, 15 minus 15 is 0. So you can change that. It's up to you. Magnitudes don't matter, so I'm going to choose to ignore it. 2 pi over 3. Okay, so 2 pi over 3 is the direction angle. So I already know that I really need bigger margins on these notes. I already know that there's no reason for me to use, hold on. Okay, so 2 pi over 3 is like here maybe. So I need a vector that is orthogonal to that. Well, what if I just kind of make a vector orthogonal to that, right? So if this is 2 pi over 3, crash. Hold on. It doesn't even know it crashed yet. We're back, hopefully. I lost my whole picture. Crud. Okay, so it was like, this is gonna be a worse picture. Well, is it? Should be a worse picture because I'm going faster, but it does not seem to be. Okay, so this is 2 pi over 3. And what I'm going to do is I'm just going to create a vector that has a direction angle that is pi over 2 away, right? So if I make this pi over 2, then 2 pi over 3 minus pi over 2. So what? 4 pi over 6 minus 3, so pi over 6. If I make this pi over 6, and use that as my direction angle, it's definitely orthogonal, because guaranteed. So I'm going to do cosine pi over 6 sine pi over 6. Like, why wouldn't I? As long, ew, gross. As long as the angle between the vectors is pi over 2, and pi over 2 pi over 3 minus pi over 6 is pi over 2, guaranteed. Could go the other direction, right? So this is going to be a little trickier, though, if I want to be like strictly correct. So I could go this way. So I'm going to add pi over 2. So 2 pi over 3 plus pi over 2 is 4 pi over 6 plus 3 is 7 pi over 6. Now, what's the problem? The problem is 7 pi over 6 not allowed to be the direction angle. But it'll work. And if I expand this, like you would never know that I use 7 pi over 6, right? Because I'm just going to get negative radical 3 over 2, negative 1/2. You can't tell what I thought the direction angle is, but I should use negative 5 pi over 6. So it's coterminal, but it's in the interval. I'm only allowed negative pi to pi. So I should do this. But like strictly speaking, they're both negative root 3 over 2, negative 1/2. So like, nobody knows. Okay, so now there's a question like, which was the easiest to figure out? You probably won't agree with me. I'm going to say that the third one, the third row, is the easiest because you already know the angles. So I'm going to say third row, already know direction angles. So we can just add, subtract pi over 2 and guarantee that we're orthogonal. I mean, the other ones, because of a trick in 2 dimensions, it's easier. But like, I don't know. I think the other one's just easier. I think it makes more sense to me. It really like, I like when things use the definition, right? Make a vector that's orthogonal. Well, orthogonal means the angle between them is pi over 2. So just add pi over 2 to the direction angle and guaranteed you now have a vector that's orthogonal. So I'm gonna stick with that. Must all vectors orthogonal to AB fall on the same line? No, absolutely not. You always know that that's not the case when there's like a hint that has to set like a different question. There's no way it could be the answer. So I'm going to say no. So what does need to be true about them though? So if this is AB, then, like you could have this would be orthogonal. I don't think I'm doing a good job of drawing orthogonal things. This, all vectors orthogonal to AB are parallel to each other. They're not necessarily on the same line. They're just parallel to each other. Because you can pick them up and move them. They don't need to stay on a particular line, but they do need to be parallel to each other. They'll all be scalar multiples of each other. So that's good to know. What must be true for the direction angle or angles of all vectors orthogonal to A, which is cosine alpha sine alpha. So this is basically this problem right here, right? So if we know the direction angle is alpha, so they have a direction angle of alpha plus or minus pi over 2. So these are like, it's good. You should go back and think about all these things, but like me spending more time talking about them, I don't think is going to help you to think about them. So draw some pictures, play around, come up with a bunch of different answers, see what you can do. Find a value of k such that the vectors are orthogonal. Okay, we can do these before we call it quits on this video. Vectors are orthogonal if the dot product is 0. So dot product equals 0. So k is 18 over -8, which is -9/4. That's it. That's the only value that'll make that true. That's interesting. Yeah, that's it, I think. Yeah, good. Maybe. Whatever. So this one you can kind of look at and see the answer, but you don't need to. You just can. I mean, the dot product is this, and we need it to equal 0. The only way that's going to happen is if k is equal to 0, which sort of made sense because this is like, well, does it make sense? I don't know, because these numbers have to be the same, and the dot product has to be 0. For some reason, I look at this and I feel like I and j are just like involved. Like I and j are orthogonal to each other. I dot j is going to be guaranteed equal 0, and I feel like that one's related to that. I don't really know. Don't know that I might not be right in the way that I feel like that one's obvious. This, we can do two different ways. I'm going to factor it and say like k minus 4, k plus 4 equals 0. You can move it over to the other side and then square root, but then people tend to forget the plus minus. Disaster. So I'm going to say either k is 4 or k is -4. So two values. So that's interesting. And then, what the heck? All right. So dot product. So k plus 2, k plus 3, plus, nope, plus, well, plus 4 times -2, so -8 is 0. K squared plus 5k plus 6 minus 8 equals 0. This feels like it's not going to factor, which is okay because it doesn't need to be factorable. It just needs to have solutions. So I'm going to use quadratic formula, I guess. So k is the opposite of b, plus or minus square root of b squared, so 25, minus 4 times -2, so plus 8, and all over 2a. So I guess we'll say -5 plus or minus the square root of 33 grows over 2. That's weird, but there you go. I mean, those work. So these, I'm going to show you really quickly. Well, I don't know if I do anything really quickly. I'm going to show you on the calculator. Calculator can actually do these problems. So I'm going to combine a lot of things. I'm going to use solve, menu 3, 1. I'm going to use dot product, which is menu 7, C3. I'm going to type in the vector. So k plus 2, comma 4. And then, oh, hold on, I'm going to type it in wrong. Comma 4, that's the first vector. Comma, because we're dot producting two vectors, k plus 3, comma -2. We need it to equal 0 because we want them to be orthogonal. And I want to solve for k. And you can see it gives you, so what is it? It gives you 5 plus or minus radical 33 over 2, but it wants to lead with the radical and then factors out the negative. I don't know what it's doing there. But anyway, it's -5 plus or minus radical 33 over 2, confirmed. So the calculator can do them, and you should try it, because if you don't know how to use your calculator, it's never going to help you. And if you know how to do some things, maybe you can work out other things. So anyway, that's this page. So I'm going to call it quits. I will see you in the next video where we will be doing some other stuff. So see you there.